All right, folks, I'm going to get started. Okay, so welcome to those on the other end. Welcome to you folks here. And then we'll just get started straight away. So today, this is lecture 6 now of my half of the Axion Cosmology course. I'm going to be telling you about cosmological data. Just to recap quickly what happened last week. So we started last week with the QCD axion, its motivations in particle theory and some background calculations. We then motivated the existence of axion-like particles in string theory and moved on to talk about where these things come from in cosmology. So we talked about thermal relics and non-thermal relics. The non-thermal relics being the most important for dark matter. We get cold dark matter either from the QCD axion, where the typical range of decay constant to get the right relic density is something like 10 to the 12 GeV, although it can be much higher or much lower, allowing for, if you allow for either moderate fine tuning or accounting for the uncertainty due to production from string decay. In this sense, we separated the axions into two camps. The cases where the Petrie-Quinn symmetry is broken during inflation and the cases where it isn't. For the QCD axion, both of these are important, and they're delineated by the value of the decay constant. The decay constant, if it's large, the QCD axion has to have its symmetry broken during inflation, whereas if it's small, that statement depends on the energy scale of inflation. For the string theory axions, we found that in the simplest case, you get the right relic density from gut scale decay constants and ultralight masses. So masses 10 to the minus 15 to 10 to the minus 22 EV. For the string axions, you actually better be in the case where the symmetry is broken during inflation. If the equivalent of the Petrie-Quinn symmetry for string axions was not broken during inflation, it would mean that inflation was a stringy, suffered from, would have to be computed using string scale physics, because for axions, that scale is really the string scale. So, and in those cases, again, we still talk about the decay constant, even though there isn't a global symmetry, but we tend to say it's close to the gut scale, and therefore normally broken during inflation. So now we're going to try and start bringing those things that we learned about along with cosmological perturbation theory in the next 2 lectures to constrain axions using cosmological data, using precision data, namely the CMB, but I'll also talk about large scale structure and galaxy formation. So before I can do that, I need to enlighten you, and I'm going to spend basically the first half of the lecture explaining what cosmological data is, because I'm a cosmologist, that's my background, and I want you to know about it too. So the selected reading here is Dodelson's book's great. For the CMB, I won't go through the calculations in much detail, but this nice paper by Seljak, a 2-fluid treatment of CMB anisotropies, is really something that you can kind of solve in an afternoon using a simple mathematical or Python code or something like that, and get out the main structure of the CMB, namely the acoustic peaks and the Saxe-Wolf plateau. So if you want to play with the CMB, this is a nice paper to read. I'm going to talk for a little while about cosmological data, and this will also come up tomorrow. So I'll talk about Markov chain Monte Carlo. This is the classic Cosmo MC paper by Lewis and Bridle. I'll talk about Foreman-Mackey's very nice MC code, because it's easy to use, not just from the CMB, but for anything that you need to use Monte Carlo for. MC is really nice and packaged. A lot of the data I will be talking about using, I currently use this code, Cosmosis, by Zuntz, which you can get here, and has a whole load of nice example problems that you can go through. And for me, the underlying CMB calculator will be CAMB by Anthony Lewis, but of course there are others, class also being very common and very useful. Okay, so what is modern cosmology? Modern cosmology is Bayesian parameter estimation from precision data. And the parameters are just some number in your model. For example, your parameter might be the age of the universe, and you want to fit that and find out how old the universe is. The estimation means applying statistics, in the most kind of naive way of saying that, I want a best fit and I want an error on a parameter. Then the data that we're using will be some cosmology, so it will be a survey of some kind of large scales. So either the Sloan Digital Sky Survey, SDSS, the Dark Energy Survey, DES, or the Planck CMB maps. And precision in this case means two things. There are small errors on the data, i.e. the CMB temperature. The maps are very well measured on very many scales. And also small errors on the derived parameters. Okay, so here's the kind of standard picture that you might be aware of the progress that we've made in cosmology in the last 25 years. So first of all, we've got the COBE satellite, which made measurements of the large scale angular power. I'll give you a bit of a longer history lesson in a few slides' time. Measured the anisotropies on 10-degree scales. WMAP came along 10 years after that, measured the anisotropies on degree scales. And then 10 years after that, Planck came along and measured the sub-degree anisotropies. Of course, this is a simplified version of the history of the CMB. Makes you think that it was all done by satellites every 10 years. Huge progress has always been driven, actually, in the CMB by ground-based experiments. Ground-based experiments and balloon-borne experiments. Did a lot in between COBE and WMAP to establish the cosmological model. I will talk about that. And the future of the CMB is very likely to be driven strongly by ground-based experiments in the coming decades, namely the Simons array, CMB stage 4, if it happens, things like this. So huge leaps in sensitivity can be done on the ground because the initial outlay of building the experiments is just so much smaller. You just have to, you can roll the technology out faster on the ground than you can in space. Okay, so in order to talk about data in cosmology, we always have to talk about Bayes' theorem. That's because cosmology isn't a frequentist. It isn't a frequentist thing. You can't do the experiment many times. You have to just make one observation and make inferences from that. So there is no way around. You can't be a frequentist and be a cosmologist. It's impossible because there's only one universe. So Bayes' theorem is just a statement about conditional probability. This is just a theorem in conditional probability. The probability of theta given d times the probability of d is the probability of d given theta times the probability of theta. It's just a theorem in probability theory. But when we think about this in terms of parameter estimation, the meaning of these different terms becomes relevant. So number one, the term on the right, on the left-hand side is what we're interested in. This is the posterior probability of the parameters theta given the data d. That's what you want. You want to know the probability of your parameter so that you can estimate its mean and its error bars. But you need these other three ingredients in order to do that. Number two is the likelihood. That's what we can actually compute. The likelihood of the data given the parameters. And I'll give you an example shortly. So you have some measured data with some data points. You have some theory curve that goes through them. By computing the distance of the curve from the data points, you get the likelihood of the data given the theory, i.e. the parameters you put in. Number three is very important, and it's something you can't get around in Bayesian statistics. And in fact, you can't get around it in frequentist statistics either. Frequentists just lie and say that they don't have priors. The prior is what you must assume. The prior probability of your parameters. And I'll talk about why that's so important later, but you have to assume an initial distribution in order to go anywhere, in order to make any progress in your parameter estimation. And 4 is normally something we neglect, but it can be very important. So 4 is just the probability of the data itself. And that is something that we use for model comparison. It's known as the evidence. If you're working within the context of a single model, so all of this actually should have given m, given m, given m. This is all in the context of one model. So if you just care about the probability of the parameters in your model, you can forget P of D, and it's just the normalization. It just comes from demanding that the integral of the integrals on the theta on both sides are equal to 1. However, if you want to compare models with different parameters, models with different numbers of parameters, The thing that allows you to compare different models is actually PD. This is what you use to compute, for example, the Bayes factor. Okay, so let's just do an example. I don't know how perfect this is. I dreamt it up a few days ago, but let's imagine that you have a thermometer. In a simple case, we may actually measure the parameter we care about. So for example, we might want to estimate the temperature of the water, given what the temperature on the thermometer says. So our apparatus, for example, the thermometer, will have been tested over many ranges by the manufacturer, and they will give us some error that you expect to have on the measurement that it tells you. And the instrument maker, therefore the instrument maker would be providing us with the likelihood. That's where the likelihood comes from. It comes from what you know about the experiment that you're doing, i.e., in this case, how well you know your thermometer. So they might give us the following likelihood, P of D given theta. They might tell us that it's Gaussian. So sigma would be the error that is provided by the instrument manufacturer. The measured value that it tells you on the instrument is D. And the parameter that you're interested in estimating is the true value of that, i.e. theta. In this case, x bar, the true value of the temperature. And sigma squared would be the error that the manufacturer has told you about from testing. In this example, you also know the prior. And this actually shows you quite nicely the role of priors, the fact that they're physical. So we need to actually know, well, what do we think the temperature of the water is? If it's water, my prior should probably be that it's a uniform distribution between 0 and 100 at room temperature and pressure. Because if I measured my water and it told me, if I put my thermometer in the water and it said 200 degrees, I would reject that because I would know something is wrong with the thermometer and not something wrong with the measurement. So the prior is important because it can get rid of things that are obviously wrong for you. And in this case, we would also probably think that we should have a uniform prior. But there are other examples of proper priors to use. You can choose least informative priors and all kinds of things like this, depending on what you know about the parameter you're measuring. In this case, we know it's water, so we know it should be between 0 and 100. But if it's some mass scale of some particle, for example, we don't know what that mass scale is, so we can't introduce a uniform prior because that already assumes the units that you're measuring it in. So for a dimensionful parameter that you don't know, the proper prior to take is a log flat prior that doesn't assume anything about the units, for example. Okay, but you also see here the role of the prior and the likelihood. So as long as S sigma is small compared to our prior, the posterior. My speaker's just done something. Sorry. Let me check. Okay, it's still in. Okay, so you see that if the error is small compared to the width of the prior, the posterior will very quickly converge. So as long as the error that the manufacturer has told me is smaller than the size and width of this prior, the prior doesn't matter. So as long as your measurement is good enough, the prior doesn't affect you. But if they had a really crap thermometer and the error is 50 degrees, the prior is important because my water might be 90, 50 degree error. They tell me it's 140. I know it can't be that. So then the prior takes over. So the prior is important when the error is large, but it's not important when the error is small. Okay, so so the way we apply this in practice. Sorry, I'm just fixing something here. Right. The way we apply this in practice is we do what's called MCMC, Markov chain Monte Carlo. Markov chain Monte Carlo is a way to apply Bayes' theorem in practice. So when you have many parameters, lots and lots of data, you can't estimate the likelihood perfectly. And we need to find the peak of the likelihood, for example, as well, peak of the posterior. So it's a way to apply Bayes' theorem for complex models and data. This is because we have many parameters We want to find the maximum of the likelihood and then estimate the width of the posterior around that. But if you have, say, 6 parameters, you can't grid very finely in 6 dimensions, because even if you wanted just 10 sample points in 6 dimensions, you would need 10 to the 6. You need to estimate your likelihood 10 to the 6 times. If estimating your likelihood involves running some kind of, even if that code takes 1 second to run, doing 10 to the 6 is already pretty hard work. So the way to do optimizing functions in large numbers of dimensions, you can't do it by a grid method, you have to do it by Monte Carlo. So the game with the Markov chain Monte Carlo is to take random samples in your parameter vector, such that at the end, if you histogram those samples, it will be representative of the shape of the posterior. So that representative bit is what the Markovian bit means here. So Monte Carlo means random samples, such that at the end the histogram is representative. It's because you have to use an algorithm that is a Markovian process. And you can look up what that means if you want. So what do? We start off, we make a proposal distribution. We draw some value of our parameters. We then do a computation. We evaluate the prior and we evaluate the likelihood. This can be intensive. This is the part where you'll have to call your cosmology code and create a spectrum and speak to some data. The likelihood could itself be a complicated function, as well as evaluating the theory prediction. So this is the bit that takes time. You then make an update. Once you know L and theta, L and P theta, likelihood and prior, you update your proposal distribution and repeat. Yeah.
So can I ask, when you draw the random theta, wouldn't it be reasonable to already insert the prior there? Draw random thetas in our water example between 0 and 100.
The point is you don't have to. The proposal distribution and the prior can be different. You don't have to draw from your prior.
And can it be advanced at some point?
Because you might want to impose a prior later. So for example, let's take the Hubble parameter. The Hubble parameter doesn't have to be a parameter in your model. So in the case of the CMB, the parameter in the model that it makes sense to vary is the angular size of the sound horizon. So you step in that between 1 degree and 2 degrees, and then Hubble is a derived parameter. But then you might want to impose a prior on Hubble, say coming from some distance measure. So then you can compute priors at a second step. So it works when you have multiple parameters, where a parameter that you want to impose a prior on isn't one that is a good orthogonal direction to step in.
So if the theta you draw from is a different theta than the...
yeah, or your prior might be some function of a combination of parameters.
Yeah.
So for example, let's say your parameters have some correlation. I want to step in them uniformly in some grid, but I know that actually some combination of my parameters is constrained, then I can impose priors in different ways. And they're just formally different things that you might want to do. Okay, and then you repeat this step until convergence is estimated. This is typically this is some kind of black magic, but I can talk about how it's done if you like. But there are ways to estimate when your algorithm has converged, how many samples you need. Just as an example, if you were doing estimation of lambda CDM parameters from the CMB, you would typically need 10 to the 5 samples or so. This is the rule of thumb I have in my head for CMB parameter estimation. But of course, you actually estimate convergence using, for example, you can use a spectral method where the spectrum of your parameters should approach a certain random distribution. If you reach the top and you're near the top of the prior, the way that it steps should become random rather than correlated. So if your parameters are still moving from somewhere in the posterior towards the maximum, then the steps in your chain are correlated because they know what the past one does as you're moving down the likelihood. But once you're at the maximum, they should become uncorrelated. So you can use statistical methods to estimate that level of correlation. Gelman-Rubin is the famous method to do this. Okay, so there are different methods that work better in different situations. The standard Markov chain Monte Carlo uses just a covariance matrix to update these proposals, so it learns about correlations. There are other ways to learn about correlations. This is the video that Dan Foreman-Mackey made to show you how MC works. Let's just have a look. I don't want the music. Okay, so he is showing the Metropolis Hastings algorithm, which is a standard one. He's trying to estimate this nasty posterior that he's put in. 1 point doesn't explore all of the correlations well, but MC allows you to use many different points and estimate more complex correlations more rapidly. So he uses many points that speak to each other in this so-called affine invariant way to learn about complex correlations, which would be very hard to do for those non-Gaussian correlations in that word with a standard Metropolis Hastings algorithm. Okay, so moving on. Now we're going to move on. We've done our statistics background. We're going to do specifically what happens in the case of the CMB. So in the case of the CMB, or in fact any variable that's measured on the sky, for example, the projected lensing convergence or something, we're interested in just an angular power spectrum, CLXY, where X and Y are the two fields that I'm correlating, and L is the multipole, which I'll show shortly. For definiteness, let's just set X equals Y equals delta T, the temperature fluctuation. So delta T is a function of theta phi, the coordinates on the sky. And it is the measured temperature minus the mean. The mean temperature is something that was measured very well by Kobe, and it's 2.725 Kelvin. In fact, you don't need to subtract the mean for the normal power spectrum measurements. The differences are taken account for. So we decompose this field delta T into spherical harmonics to reflect its symmetry. So delta T theta phi is just a set sum of a multipole moments, Lm. YLM, where these are the spherical harmonics, which contain the angular dependence, and then we need these coefficients, ALM. So the coefficients in the expansion are the thing that we actually measure. So you take your map, you take that you take that spherical transform, and your map tells you what ALM is. So we get L plus 1 different M values for any single value, for any single multipole L. And that's just the number of different Y's that there are. And so then we define our quantity CL to be this expectation value, ALM, AL prime, M prime, with the appropriate Kronecker deltas. The average here is the angle average. So the average is taken over M. And this is the thing that will relate to the theory case later. CL is the thing that we call the power spectrum, and the power spectrum is just the variance of the distribution of these ALMs. So for my map, let's say I'm looking at L equals 50, then I get about 2,500 different values of ALM, and I can just histogram them. They should have 0 mean and standard deviation given by square root CL, if they're Gaussian distributed. And that's this, that's the cartoon of what this looks like from Dodelson. So here is your ALM distributed around 0, and the probability distribution of ALM for a large enough L will look Gaussian, and its variance is just square root CL. So this is how you get a measurement of CL and an estimate of the likelihood of CL. So it's distribution. You measure this distribution ALM, and this approach is a Gaussian for large values of L, but it's non-Gaussian at low L. So the power spectrum measures the amount of correlation in the temperature on a given angular size L. So the theta dependence of Y tells you the angular correlation in this patch, represented by an angular scale L. So how do you relate this to our theory? So now we know how to measure CL and measure the error on CL, but we need to know how to compute CL from theory. So using a property known as ergodicity, we can replace the angle average, the M average, which is the thing that we can measure. We look at one universe, but we measure many different M's. So we get an average measurement of CL. Using this property of ergodicity, we can relate the angle M average to the theoretical ensemble average. So what we compute is we get some random realization of our universe from a power spectrum, and we want to know the ensemble average of many universes, but we relate that ensemble average to the angle average using this ergodic property. And this is what leads to cosmic variance. If we don't have that many M's that we can measure on the sky, we don't get a very good estimate of the true ensemble average because we don't have enough modes to measure it with. This is the origin of cosmic variance. Because of what we talked about last time, where we have this linear theory and we just compute transfer functions, this is very handy because we can separate out this statistical part from the transfer function. This is what I talked about last time. So X is our field that we're interested in. It has some stochastic initial conditions, xi, carry all the statistical information, and then it has some transfer function. And this transfer function, I'll just remind you again from the discussion last time, this is a transfer function of a coupled system. So we have many, many fields that we're evolving: the photon density, photon velocity, dark matter density, baryon density, etc. And so this is a transfer function of a coupled system with time-dependent coefficients. And so depending on how we start the system off, in what mode, this transfer function will be different. And from the discussion last time, and this is what we'll talk about at the end, the transfer functions are different for, importantly, the adiabatic mode versus the isocurvature mode. So these things have different shapes depending on the initial conditions. So then we can take our ensemble average. Theoretically, we can take the ensemble average of our two fields x, y with wave vector k and position p hat on the sky. We take that that ensemble average and replace it with the ensemble average of the initial conditions times this transfer function that in this case is just a product. So you can then use this to construct CL, the angular power spectrum of whatever you're interested in, these two quantities x, y. And it is given in the following way, where P of k, it comes from the statistical averaging of the initial conditions, and delta L x, y is the transfer function in this case of the two fields x, y. So this is just what I've said. We have an initial power spectrum and a transfer function that's specific to both x and y, the fields that you're correlating, and the mode for which you're interested in, adiabatic curvature. So, but what is this transfer function? So the transfer function is the thing that contains the physics. So I'm interested in the transfer function delta t, but I need to know what in my system can give rise to temperature fluctuations. So I need to work out what ingredients there are in this temperature transfer function or polarization transfer function, for example. For temperature, I can just write this down for you. This is delta T over T, expressed in terms of the C and B variables. And then to get the transfer function, I just square this thing. So this is delta T over T. What are all these different pieces? Well, first of all, there's some notation. Well, first of all, I should say, actually, this is the unlensed delta T over T. Lensing is something that we do to this afterwards. And I'll give a bit more detail in lensing next lecture. Is the unlensed temperature power. Next, there's some notation. N is the direction on the sky. What was p hat in the last slide? Sorry about that. N is the direction on the sky. This is just a two-dimensional vector. Mu is the opacity, and I'll show you how to compute that very shortly. Okay, but now the physics of what actually leads to the temperature anisotropies. So the thing in the brackets is the thing that creates the temperature anisotropy on the sky at last scattering. Then the mu dot e to the minus mu d tau is the integral of what happens to that photon along the line of sight. So the photon gets scattered because the universe isn't completely, what's the opposite of opaque? Isn't completely transparent to photons. The photons can get scattered along the line of sight, and that's what the integral d tau conformal time e minus mu is. Okay, so we need to create photon fluctuations at the surface of last scattering. So we have the gravitational redshift to start with. The photons have to climb out of whatever potential well they were in. We then have the photon density, just how many of them were there. We have the Doppler effect, because the photons are moving relative to the baryon plasma. So the rest frame is the rest frame of the plasma. The photons have some Doppler effect. And then we have this relativistic effect, because it's proportional to the time derivative of the Newtonian potential. And this is the integrated Sachs-Wolf effect, or the Sachs-Wolf effect. So why do we need this combination? Why can't I just say how many photons are there? It's because, as I stressed in the last lecture, the photon density is not gauge invariant. If I change gauges, change from Newtonian gauge, synchronous gauge, the value of this thing, delta gamma, would change. But this combination is gauge invariant. So that's why you need to be careful to do this. So this is actually unobservable, delta T over T.
Why is it proportional to the opacity time derivative first factor?
Why is there a mu dot into the
mu
minus?
is opacity?
Mu is the opacity, but you have to integrate it along the line of sight. So this would be like d mu by dt d mu. Right, I think, if mu is the opacity, maybe e to the minus mu is the opacity, and this is d opacity by dt. Okay, because this is obviously d mu by dt, so we are integrating d mu really, from where you started to where you ended. Okay, so the opacity is given by the Thomson scattering of photons off of free electrons. So where mu dot is A, where A is the scale factor, sigma T is the Thomson cross section, XENE is the free electron. This is the number density of electrons, and XE is the ionization fraction. So if the universe is ionized, it's opaque. And if there are no free electrons, then it's transparent. So this is the thing where we need some additional physics to sit on top of this. We need something other than just Friedmann's equations and the equation of motion for the photon over density and things like that. We need a model for how XE, the free electron density, evolves over time. We can do this very well at recombination. So if all that happened was the universe was a plasma and then it became transparent at recombination, then we could replace the integral mu dot e to the minus mu d tau with just a delta function at the surface of last scattering, and then the photons freely propagate. But recombination has some width, which we have to include. And then there is an additional change in the free electron number density caused by reionization, caused by galaxy formation. And in general, in a CMB code, you just put a simple model in for reionization. You assume that it just has some average optical depth to reionization. You may also, nowadays, you're sensitive to the location and shape of reionization. But at zeroth order, all you need to know is the total optical depth. So that can be kind of stuck on at the end as part of your model. Okay, so, I didn't bring my notes with me. Okay, well, I'm going to tell you now on the blackboard for a minute about the anatomy of the CMB anisotropies. So hopefully everyone can see the blackboard, and hopefully I just remember what I was going to tell you in my notes. So this is just because it was hard to do this annotation. This annotation would have been messy on a slide. I'm just going to draw what the CMBCLs look like and just explain roughly what the physics is that's going on. So here I'm going to use BL, which is LL plus 1 CL over 2 pi, and it has units microkelvin squared. And on the x-axis, I'm going to use multipole moment L. Okay, and then this is what the CNBC looks like. Next is some flat piece and some acoustic peaks. So let's talk about these different things. So this is the first peak. The first peak is at L of a few hundred, and it corresponds to angular scales of order 1 degree. First peak, this angular size is related to the angular size of the sound horizon. So, what do we need? We need theta, which is the ratio of two sizes. So it's the size of the sound horizon divided by the distance to the surface of light scattering. So this tells us, remember we had this strongly coupled photon baryon plasma, and in that there were sound waves that could propagate when the photons and baryons are coupled, so they have some distance that they can travel. And the angular size, so here is some snapshot of the surface of light scattering. And I start off with some density perturbation. Sound waves will travel out from it. They will reach some size before recombination happens, and after that they will freely propagate. So it's this angular size, theta. So it measures when recombination happens. Essentially, this sound horizon. We've got this physics here. Now, at large angles, this is called the Sachs-Wolf plateau. This is the bit where if I replaced my delta functions in the expression for delta t over t, there would still be some processing of that afterwards by the because of the phi dot term, the time derivative of the Newtonian potential, and then also reionization when my opacity is not a delta function. So here we see a number of different things going on, but there's obviously not many features. We've almost got a good shot of the primordial power. This is basically the primordial amplitude plus some small evolution. But we've got in here effective reionization. And we've also got effects of the time derivative of the Newtonian potential. That measures dark energy dynamics. In Newtonian theory, phi dot will just be 0. So the time derivative of this depends on relativistic effects. So it measures relativistic effects, it measures reionization, and it gives us the amplitude of the primordial power appropriately normalized. This is all interesting, but there aren't very many modes. The other thing that we learn about the large-scale universe from the CMB is in this term dLs, this angular size of the sound horizon. So we got RS gave us the redshift of decoupling, but then we also need to know the distance. The distance to the CMB. So this quantity, the angular location of the peak, tells us how far away the CMB is. So we also get some sensitivity to things like H naught, the equation of state of dark energy, things like that. Curvature, very important. Okay. The overall shape, having this large first acoustic peak, as I'll show in some different slides. So the overall shape with first peak tells us the mode traffic. So the transfer functions I said are different for different modes. So the overall shape is determined by the mode, i.e. what transfer function you're using. This overall shape with a large first peak only occurs for the adiabatic mode. So this tells us whatever we're seeing is dominantly this one mode of initial conditions, which is very important for the rest of this lecture. What about the higher acoustic peaks? What do they tell us about? Well, they tell us about how much these sound waves were damped. So especially the higher peaks are called the so-called self-damping. So there's diffusion damping in this plasma, and how much damping there is the self-damping. This is all, everything to the right of the first peak is established by sub-sound horizon physics in the very early universe. And so a lot of this damping and things is measured by, it depends on the expansion rate at early times. So this damping measures what's going on during the radiation era in terms of the expansion of the universe. So we get measures of the effective number of relativistic species. We've seen this in lecture 3. And particularly the relative height of the second and third peak measure the baryon density and the cold dark matter density. They're very sensitive to these two quantities. They're sensitive to what's going on in the expansion rate between decoupling and matter radiation equality. Hence omega B, omega C. Self-damping, we measure things like N effective. We're going to use this later to measure the axion density and mass. Okay? And then there are kind of what are called normally secondary effects, but become increasingly important once we've measured this overall structure very well. There's a blurring of peaks. I said I only showed you the delta T over T unlensed. There's additional processing that happens to the temperature anisotropies as they propagate to us, even on small scales, caused by the lensing of galaxies. So this angular scale of galaxies, for example, is smaller than the angular scale of the CMB. So the CMB can get affected on its smaller angular scales by lensing due to clusters, for example. This blurs the acoustic peaks in this picture. Lensing, and that gives us some measure of the growth of structure. And we'll talk more about lensing in a different context in the overall lensing power spectrum next time. Okay.
So for the other,
Yeah, all the peaks are blurred. In particular, actually, lensing and silk damping almost remove the peak structure entirely at very high L. I haven't included here a secondary anisotropies, which, so this L that I've shown here would be a maximum of a few thousand. At L approaching 10 to the 4, secondaries come in. Secondaries and foregrounds. Secondaries, for example, the kinetic Schumacher-Dovich effect. And lensing causes the higher tail of the CMB. Eventually, it goes over from kind of a peak blurring to just a power law contribution to the anisotropies. So, yeah, the character of lensing changes a little bit in the higher peaks, but the peaks eventually go away due to the silk damping. Anyway, and get overtaken by secondaries. Okay, so that is our anatomy of the CMB. Hopefully you get some sense of how all these different bits of physics appear, how they all came from that transfer function, the phi dot, and how we measure things like the gravitational potential, the total matter content at the surface of last scattering, and how everything depends on the expansion rate during the different eras. Okay, so I'll now return to my slides. Okay, so here we are. We've had a look at the anatomy of the CMB. let's have a look at how that is used to measure cosmological parameters. So let's have a little look at a case study of lambda CDM and Planck. So the theory space here would be 6 parameters of standard lambda CDM. They include things about general relativity, the initial conditions, and the matter content. The computation involves solving the Boltzmann equations, this coupled fluid system that we looked at before, doing a Monte Carlo over solving that system with many different sets of parameters. And the data is the CMB temperature power spectrum. In the Planck, I think 2013 paper, they give you this horrible map of what they actually do to get the constraints. But from the point of view of a theorist who's just given the power spectrum at the end, we can simplify this. So we start with some map of the sky with some temperature anisotropies measured on it. This is the map of the sky with the galaxy masked out and then reinserted with a constrained realization. So you can't see the galaxy. So here it is. Here's the temperature anisotropies measured in kind of 500 microkelvin. We take the correlation function and the Legendre transform of this and get the CMB angular power spectrum. This is what I drew before. DL in microkelvin squared, multipole moment, angular scale, first peak, etc. The data points are now what you've measured from that process, and the error bars on them, at least at high L, are just the measured from the distribution of the ALMs. Estimating errors at low L is a little bit more complicated. Now you just need to compute the theory spectrum, i.e. the green curve, and Monte Carlo over that for your many different parameters for which the shape will change, and apply Bayes' theorem. When you do that, you extract some best fit parameters and some errors. So these are, again, I think the Planck 2013 measurements that I'm showing you here. Here are your 6 parameters: omega baryon h squared, omega ch squared, 100 theta mc. This is the angular size in radians of the first acoustic peak. Tau, the optical depth to reionization. We have to include that additional damping, but it's just from one parameter here. So we've got matter content, omega baryon, omega c, angular size of the first acoustic peak, the thing measured here. That measures the distance to the CMB, so that's your parameter that encompasses how much dark energy there is, 100 theta mc. Tau, the damping, something you cannot ignore. It's very important for the relative size and the temperature and polarization, which I haven't talked about. And then your initial conditions, NS and log 10 to the 10 AS. I'll explain those parameters shortly. But the point is, these parameters are all measured with the best fit and have some pretty good small errors, all pretty much sub-percent as far as I can tell. Tau having the biggest error in this case. And then you can infer a lot of other things about the universe. You can compute lots of derived parameters. Here they show a selection of derived parameters: the dark energy density, omega lambda, sigma 8, the galaxy power spectrum normalization, H0, the Hubble constant. The age of the universe here is a derived parameter, 14 billion years, and things like this. They're all derived, they're all things that you can compute given the model from these 6 parameters. Okay, this lovely story of the CMB, I like showing these slides because for people, you know, my age and younger, we've just always had, well, for me, we've always had WMAP, and the WMAP power spectrum always looked like this, pretty much. Larger errors on the 3rd, 4th, etc. acoustic peaks, but this is always how the universe has looked. And we've always had 6 parameters, and they've always been, you know, measured relatively well. But this obviously wasn't always the case with the CMB, and I like to show how far we've got. So these are slides taken from Lyman Page's website, and his book was Peebles, Page and Partridge, called Finding the Big Bang. So they're showing here not the CMB power spectrum, but just the temperature amplitude in multipoles as a function of multipole moment, measured by many different experiments, and the current best fit theory spectrum as a line here. So these are the measurements taken between the discovery of the CMB in 1965 by Penglis and Wilson and 1979. People were trying to measure the anisotropies even then, but no measurements were consistent with a non-zero anisotropy. But they were even measured on small scales. I think this was the Green Bank telescope, Parkes Radio Observatory, things like this. Moving on to 1980 to 89, you start to get some kind of meaningful sounds, maybe even some claimed detections of large-scale anisotrophies, but at much too large amplitude for the current theory spectrum over here. Suddenly, we start to get early detections in the early 90s, correlated fluctuations on large scales. Now you see the error bars have shrunk a lot, and we can really, compared to the current best fit spectrum, the errors are starting to get close. DMR2, DMR is a COBE measurement, FIRAS, and I think this is FIRAS, or no, maybe it's not. You're starting to get some detections. This is the early days of COBE, but people are also maxima trying to measure this rise, but they're not conclusive. And SK1, this would be the a Saskatoon balloon-borne experiment, also starting to make this detections on large angular scales. 1994, COBE DMR4, very well established measurements of the amplitude of the power spectrum on the largest angular scales. This is why for a long time people called the amplitude of the power spectrum COBE normalization, because COBE measured it very well. But even at this stage, we're also starting to see relatively good evidence for a rise and a first acoustic peak. So people now would already be thinking, maybe this is an adiabatic mode, maybe we're going to see the sound waves, but they didn't know yet. All bets were off at this point. This transfer function with the acoustic peaks is only present if you have an initial condition way before radiation domination that starts the universe, and then you have free propagation. The spectrum using, say, a cosmic string initial condition, not inflation, does not have any acoustic peaks and literally just falls off on large scales because the strings are dynamically generating structure. There isn't an initial condition and free propagation. So people were really already thinking, hey, inflation, acoustic waves, maybe even the adiabatic mode. But you don't have this first peak very well measured. This now all changes in the late 90s. Saskatoon, Toko, Maxima. These are all balloon-borne experiments and experiments on the ground. So this is showing the importance of things other than satellites. You're starting to measure this. There was a big leap in sensitivity in the 2000s. So these are more boomerang experiments. Even start to see the higher acoustic peaks measured by Maxima. But it's not very good. Maybe you can't get parameters out of this. But cosmic strings are certainly dead now. Inflation and the adiabatic mode are the only game in town because you've seen the first peak. Precision cosmology happened before WMAP, 2001, 2002. This is boomerang, Maxima, really start to measure the higher acoustic peaks. This is now clear that the current cosmological model is going to be the right one. WMAP then comes along and makes this better, and then we have the story that we're all more familiar with. Up to today, where these are, a combination of Planck and ground-based experiments, ACT, SPT, etc. Here are all the lovely acoustic peak structures, not just in temperature, but in EE polarization, autocorrelation, even the BB power on large angular scales, small angular scales, which measures lensing, and the cross correlations and the lensing. So this is just everything now with lovely small errors from Planck and contemporary experiments. It's quite nice. This is from the Planck 2018 paper about how we measure the parameters. So this is a collection of beyond LCDM parameters. So pre-WMAP, you could even try, so they took this combination of data like Lyman Page has from pre-WMAP and extended beyond 6 parameter lambda CDM, because we're interested in other things like neutrino mass, number of effective relativistic species, equation of state of dark energy, curvature density. You could constrain this with pre-WMAP data, but the constraints weren't very good. So the neutrino masses could be, many times more than electron volts. The number of relativistic species, we talked about this in lecture 3, could be as large as 8. You just didn't have any idea. WMAP makes a big leap in these things. You start to be able to get values of these parameters centered around the standard values, slightly larger than 0 for neutrino mass, 3 numbers of species. You're centered on the right values, but your errors are still large. And then Planck is just this huge improvement, particularly on the number of relativistic species. You can see that's obvious. That's because Planck measured the higher acoustic peaks and this effect of silk damping the expansion rate in the radiation area. They weren't measured. The WMAP and pre-WMAP experiments tanked out at the third peak. So it's really small angle CMB that gives you these constraints on the beyond LCDM parameters. This brings us on to axions, because now we can say they're in a beyond LCDM parameter. They have modified initial conditions in this isocurvature mode, and if they're very light, they don't behave like cold dark matter. So these are two things that we can try and constrain about axions using the CMB, their initial conditions, and if they're light enough, their mass and their density. So in this part of the lecture, today, I'm going to be talking about isocurvature and inflation. Some reading for that is Fox, Pearson, Thomas, Hertzberg et al. And you can see this in my review. Okay, so this is kind of your 0th order, if you like, constraint on axions. I'm just going to treat them completely like cold dark matter, and we're just going to constrain their initial conditions, the isocurvature mode, and it just comes from the shape of the CMB, and really the first peak and the plateau, so it's quite easy to see where it comes from. So, remind you about the axion initial conditions from inflation. And it gives us something very important about axions, actually. When was the Petre-Quinn symmetry broken? It's the only way we can get a handle on this very high energy physics. So, recall that inflation gives us vacuum fluctuations to all massless fields. The axion is a massless field. We get this isocurvature mode. The amplitude of the axion field is the Hubble scale during inflation over 2 pi. Other massless fields also pick up fluctuations from here. For example, the tensometric perturbation, the amplitude of the gravitational waves, delta H, also goes like H over 2 pi. This is where we can get some really interesting statements about axions and inflation. These fluctuations, the axion isocurvature mode and the tensor mode, source 2 new modes in the CMB, in addition to the scalar adiabatic mode, which means we get 2 new transfer functions we have to compute, say, for delta T over T. So both of these modes, both the isocurvature mode and the tensor mode, source every type of fluctuation in the CMB. Both of them source temperature, E mode polarization, B mode polarization, and lensing convergence kappa. And the amplitude of the power spectrum goes like the square of the initial conditions. So both of these modes will source a whole bunch of different CMB modes with amplitude proportional to H squared. I want to give a note of caution here. People tend to say that measuring the tensor mode corresponds to measuring the B mode of polarization. But this is not true, and therefore they tend to think that a B mode is a tensor mode. This is not true. The B mode is the only thing, the large angle B modes are only sourced by tensor modes, but tensor modes also source T and E and kappa. And B modes are also sourced by non-tensor physics. They're just at a suppressed amplitude on large scales. You can also source a B mode from interactions. So for example, from Faraday rotation, which has nothing to do with tensors, that also sources B modes. So yeah, B modes are not equal to tensor modes. And it's important to keep this in mind sometimes. So what do those mode functions look like that I've been talking about for so long now? So here are a whole bunch of different modes that we could have in the CMB. We have the usual adiabatic mode with the strong first peak. And this is the really important thing. None of these other modes have a strong first acoustic peak if you fix the large scale amplitude. So the different modes I'm showing here are axion isocurvature, the uncorrelated isocurvature mode, the baryon density isocurvature, the neutrino density isocurvature, the neutrino velocity isocurvature, and the tensor mode. So this is the point, right? Tensor modes source scalar perturbations, delta t over t. Or rather, they don't source scalar perturbations, they source delta t over t, which you can measure. So the tensors, the pure tensor initial conditions, we would still have delta t over t, but it would fall off like this, have a large amplitude and then fall away. This looks somewhat similar to the isocurvature mode. The interesting thing here is only the neutrino velocity isocurvature mode has anything like a first acoustic peak. So none of these modes are degenerate with the adiabatic mode. We see the first acoustic peak, then we can just limit these because we know they have to be subdominant to get the right large angle normalization. But the neutrino velocity mode is the only thing that can destroy that statement a little bit. But it's a very weird mode and nobody knows. There's no early universe model that sources the neutrino velocity mode. But once you allow for that mode, then some of your constraints get a little bit more correlated. We're just going to be focusing on the tensors and the Axion isocurvature mode, which clearly have no first acoustic peak, so they're clearly subdominant. Okay, this is the statement I made about the B modes getting confused with tensors. The B polarization power spectrum on large angles only has tensors. So people say tensors equals B, yeah, because if you measured B on large scales, you would be seeing tensors. But all the other modes source B on small angular scales, large multipoles, due to lensing. Lensing turns E polarization into B, it rotates the polarization. So the scalar adiabatic mode has BB, but it has it only on small angular scales. This has been measured very well now. And as you increasingly don't measure large angle B, the tensors will eventually drop even below the lensing. So then you have to worry about things like de-lensing. But all these modes source B as well. Okay, so we want to use this measurement of the shape of the power spectrum to tell us about inflation and initial conditions. So what do we know about inflation and initial conditions? So in inflation, we have to define quantities in relation to a certain scale. So we pick a normalization scale. We call this the pivot scale. So we measure quantities in relation to when the pivot scale left the horizon. So we say, okay, when did things go classical? When can I just evolve classical evolution? That's when things exit the horizon in inflation. And so we calculate when scales leave the horizon. The pivot scale is a matter of convention, but you just fix it and then everything else is relative to it. Often it's picked to be 0.02 inverse megaparsecs, sometimes 0.002, sometimes it's chosen to be 0.05. It's just a convention. And the observables that you compute in inflation are observed to be power laws away from this point. So our initial power spectra that we said we can just factor out are generally just power laws away from some pivot scale. And that's because inflation is the soft breaking of de Sitter invariance. And that's why you get a power law. So inflation, we can then describe it by 3 parameters for slow roll inflation. The Hubble scale when this pivot scale left the horizon. So this just shifts according to our normalization. So H inflation, the Hubble scale when this mode left the horizon. And then 2 slow roll parameters that describe the soft breaking of scale invariance. These 2 slow roll parameters are conventionally called epsilon and eta. And these 3 parameters are what we can relate to observables in the CMB. So for example, the scalar adiabatic mode is expressed in the following way in terms of these parameters. It has an amplitude, which is given by H inflation over 2 epsilon. And then it has a power law in the power spectrum. The index of this power law depends on both slow roll parameters, epsilon and eta. But we've only now constrained 2 parameters of the inflationary model. We've constrained some combination of H and epsilon and some combination of epsilon and eta. But we haven't constrained, just H or just epsilon. So only the adiabatic mode has a large first peak, so we know it must be dominant. So we can use the amplitude of the first acoustic peak and the amplitude of the plateau to basically fix this AS. And then even with temperature alone, even with just the temperature anisotropies, we can therefore limit the contribution of all the other parameters, because if we add them in, we add in any other mode, it will increase the large angle power spectrum and eventually increase it beyond its observed level, because we fix the adiabatic modes, you know, fixed contribution to large angle and a fixed amplitude of the first peak. So even with TT alone, we can place a constraint on, say, the tensor amplitude and the isocurvature amplitude. So this is, again, this is what the power spectrum looks like. It has this first acoustic peak and this plateau. Planck also gives us all the other spectra. And so when I actually get a constraint, it's a combination from all of these. So there's TT, there's also EE, TE, and kappa kappa lensing. All of these things have to match. If you have just the adiabatic mode, they all match perfectly. If you add in any other mode, you'll ruin all of this. So all the other modes have to be subdominant. Okay. So if you do that with just the scalar mode, we take the combination of all the data, temperature, polarization, lensing, and using the galaxies to measure the baryonic acoustic oscillations, you get a very nice constraint on the amplitude. The amplitude is 2.1 times 10 to the minus 9. This is the famous statement that the temperature fluctuations are avoided 10 to the minus 5, because 10 to the minus 5 squared is about 10 to the minus 9. And then you also measure this power law of the initial conditions, and the NS takes this value that is less than 1. So it's a red power spectrum. It has less power at high K than it does at small k, and it has this value 0.96 for the index. The tensor modes have an initial power spectrum. So the tensor modes have an initial power spectrum that looks like this. And it only depends on the slow roll parameter epsilon. So I have an amplitude, which is the scalar amplitude times some factor of epsilon. That's because my amplitude of the tensor mode does not actually care about epsilon, it just measures HI. So the amplitude will, in this way of looking at it, just looks like epsilon, determined purely by HI, and then the running of the tensor power spectrum, which is just parameterized in this conventionally different way. So we can then try and measure and constrain this tensor to scalar ratio by just taking the sum of our power spectra and comparing them to what we measure. So the total CL will be the contribution from the adiabatic mode plus the contribution from the tensors. And if you include this now, you know, this B power spectrum, you will improve the constraint, but you can get a constraint on the tensor to scalar ratio just from temperature. It's quite easy to understand, I think. But including, of course, all your different spectra improves your error. So this is what you get as the constraint on the inflationary parameters from Planck 2018, including the large angle B's from BICEP. So here we go. You get a constraint on the Hubble scale during inflation. It's less than 7.8 times 10 to the 13 GeV. So this is the thing that tells us all axions with a decay constant larger than this value had their symmetry broken during inflation. And then here is the constraint on the tensor scalar ratio as a function of the scalar spectral index. The scalar spectral index is very well measured, close to 0.96. The tensor scalar ratio is consistent with 0. Planck alone, not using B modes, gets you this grey ellipse. Tensor scalar ratio less than about 0.1. Including the B modes improves your constraint, but not actually by a huge amount. Including the B modes, R is less than about 0.07 or something at 2 sigma. These are a bunch of different inflationary models, so you can see what you have to lie inside the ellipse to be consistent. You can see which ones are consistent. I said I'm not going to talk about Axion inflation in this lecture course at all, but just to show you where it is. This purple band is Axion inflation, so-called natural inflation in the cosine single instanton potential. Only just about consistent with Planck plus BICEP results. So the band is, this parameter has one this model has one additional parameter in addition to these two indices, so it's a band. And then these these monomial potentials here, these two red ones, are characteristic of so-called axion monodromy. Axion monodromy also just about consistent. But the point actually here would be to say that axion monodromy was cooked up to give large values of the tensor-to-scalar ratio. So it's not like this was something that was around already. It was made to sit exactly here. And so as R gets smaller, it gets ruled out. In models of inflation using, for example, string moduli, sit on these hilltop quartic models and somewhere down here. So now we want to constrain the parameters of our axion model, finally, in the last 20 minutes. So the iso-curvature mode also has an initial power spectrum. The initial power spectrum of the iso-curvature mode just looks like this, quite similar to the tensor power spectrum. I have a different convention for the indices, but that's just what's adopted in the literature. I have the same pivot scale, and now I have my amplitude of the iso-curvature mode. This is the thing that we're going to really constrain, and it has the following form for the axion iso-curvature mode. It depends on the axion relic density. If there was no axion dark matter, this mode would not contribute. So it's just proportional to the relative amount of axions in the dark matter. It's also proportional to the initial conditions. So the amount that, because this is a delta phi over phi power spectrum, it's a power spectrum in the overdensity. So it doesn't just depend on the Hubble scale during inflation, but it depends on actually the value of the axion field itself during inflation. But we know from lecture 4 that omega A is a function of phi I in the axion mass. So I can eliminate this phi I and write this amplitude as a function of the axion density and the axion mass, if I want to. Okay, so axion dark matter, this is a very important point. Axion dark matter provides information about the early universe. And the iso-curvature bounds constrain the way in which we can fit axion dark matter and inflation together. So we can use measurements of axions, if they exist, to tell us about physics going on very early in the universe and the relationship between the symmetry breaking and the initial conditions, i.e. inflation. So it's a powerful tool, if it exists, to tell us about the very early universe. And I'm going to try and give you a sense of that in the next few slides. So the axion type iso-curvature is totally uncorrelated iso-curvature. There is another type of iso-curvature called curvaton type, which is totally correlated. They have different values of the constraints. What I mean by totally uncorrelated, I have some inflaton field chi, which sources the curvature zeta. The inflaton gives me all the curvature. The axion doesn't interact with the inflaton. It was this flat direction in the potential, if you remember this cartoon that I had in lecture 3. The axion has no interactions with chi. Thus, the 2-point correlation function of the axion field with the curvature must vanish because it doesn't interact with the thing that gave me the curvature. The curvature comes purely from chi. Phi doesn't interact with chi. This correlation function has to vanish. So that tells me that the cross correlation CL adiabatic iso-curvature is 0. So I want to take my my CL. I'll draw this on the board. Hopefully those on the other end will understand what I mean. So my field, say delta T, I can now write it as my initial condition X iso-curvature times the iso-curvature transfer function plus the initial condition adiabatic times the adiabatic transfer function. And then I'm interested in correlators delta T, delta T. So I get a X adiabatic squared, T adiabatic squared plus X iso-curvature squared the isocurvature squared. So this is CL adiabatic plus CL isocurvature. But then if there was a correlation between adiabatic and isocurvature, I would get some X iso, X adiabatic, two of those, T adiabatic, T iso. But because the axion field is not correlated with the inflaton field, this cross correlation X adiabatic, X iso vanishes. So my total CL is just the sum CL total equals CL adiabatic plus CL iso, as you can see here. Okay, so it's very simple. And therefore we just get bounds on the isocurvature amplitude from the amplitude of the Sachs-Wolf plateau and the amplitude of the first peak being consistent with this being with the Sachs-Wolf plateau dominantly coming from the adiabatic mode. When you do that, you can do it in temperature, but you can also do it in polarization and in cross correlations and in lensing, and that's what you just stick all the plant data together. This is handled for you by those codes that I talked about, Cosmosis, for example. The constraint on the isocurvature to scalar amplitudes is that the relative contribution of isocurvature is less than 4%, less than 0.038. So now we just turn this constraint into constraints on the parameters in our model. We constrain this combination of parameters with the axion relative density and initial conditions, and Hubble scale during inflation, very importantly. So let's start looking at we're going to look at this in detail for the QCD axion. You can translate it to ultralight axions and fuzzy dark matter. We go through it in a couple of papers of mine that I mentioned on the selected reading slide. But let's do the QCD axion because I think it's most informative for the case of the QCD axion. So we only get this isocurvature mode in this scenario B, where the Petrov symmetry is broken during inflation. Let's consider scenario B. And let's say I just want the initial misalignment angle of my axion, my one parameter, apart from the decay constant. Let me just set that to 1. And I'll show you what happens when I take it away from 1 in a few slides' time. So then axion dark matter has no free parameters once I fix the relative density. So I fix the relative density, that fixes the decay constant. It now has to be about 3 times 10 to the 11 GeV. The axion mass is 20 micro EV if the misalignment angle is 1. So now I just substitute these parameters into my expression for the isocurvature amplitude, and I can derive a constraint on Hubble during inflation, just using all the formula I've given you in the last few slides. This is the bound they get. The isocurvature bound translates directly into a bound on the Hubble scale. Just like our tensor modes did, if the QCD axion in scenario B is dark matter, misalignment angle 1, get a bound on the Hubble scale during inflation. Less than 0.86 times 10 to the 7 GeV, and I reinserted the scaling with decay constant from the relative density. This is many, many, many orders of magnitude smaller than the corresponding bound from the tensor to scalar ratio. And this is like really the key to all of this. So would it be possible to measure a tensor to scalar ratio consistent with this value of Hubble? The answer is no, but why? So let's look at how well we could conceivably measure the tensor to scalar ratio in the near future or very distant future. So we use some forecasts that have been made. These will have been Fisher matrix forecasts, for example, or maybe a little bit more complicated, the sky realizations. So CMB stage 4, which is this proposed future array of ground-based CMB telescopes. The Simons Observatory is a step along the way towards it. So this would be upgrades to the Atacama Cosmology Telescope, South Pole Telescope, BICEP, a few others maybe in the Atacama Desert as well. Combining all of these around the world with next generation technology, tensor to scalar ratio can be measured with an accuracy of 10 to the minus 3. You can do better if you allow yourself a bit of fantasy. This is the best fantasy prediction I've seen. if you use the power spectrum of the 21 centimeter line of hydrogen, you measure the amount of lensing of that power spectrum, and you do various things. I think you de-lens the CMB and then you combine it all together. You could conceivably, cosmic variance limited, measure R at an accuracy of 10 to the minus 9. Can you ever actually measure R, not 0, but with this precision, consistent with the value, with how small we know Hubble has to be if the QCD axion in scenario B is the dark matter? So I've got a couple of slides to try and show you this. So this is a plot from my review. It's a little bit busy. I wish I'd made it better. So I'm plotting the QCD axion as a function of its isocurvature, scenario B as a function of its two parameters: Hubble scale drone inflation, axion decay constant, and GeV. At large values of the Hubble scale during inflation and small values of F, Peck-Schick symmetry is unbroken during inflation. This is scenario A. So scenario A, all this region up here is completely consistent with any measurement of the tensor to scalar ratio because it doesn't have isocurvature modes. There is no bound on the Hubble scale during inflation up in this corner here. So low axion decay constants can have any value of, can have large values of the Hubble scale during inflation. I can translate, using my bound on the scalar amplitude, any value of Hubble during inflation to a value of R. And I've drawn on here the values of R from the bicep limit, the 10 to the minus 3 order of magnitude improvement from CMBS4, and then the 10 to the minus 9, 21 centimeter lensing. So in the scenario A, values of axion decay constant below about 10 to the 14 GeV. These are consistent with large values of R because you're in scenario A. There's a slight complication due to the relic density that actually forces scenario A to have F less than about 10 to the 12 GeV. But everywhere here, fine, you can have whatever you want.
Sorry?
Yes.
What's your fiducial value for T now?
I'm just saying, what would the value of R of T be for different values of H inflation? So the region that could possibly be measured with future experiments is purple.
Okay.
So this would be like, this would be the upper bound from bicep. So the fiducial value of R is 0. And then the upper bound that you get with bicep
10 to the minus 3.
is 10 to the minus, well, 10 to the minus 1. CMBS4 is 10 to the minus 3. 21 centimeters, 10 to the minus 9. So the fiducial value, yeah, the fiducial value of HI is 0. And but I'm not using a Fisher forecast here. I'm just reading off the 95% from other forecasts. Okay, and then I say, okay, in the rest of this plane, large values of FA or small values of H, the QCD axion has to be in scenario B. Okay, then I draw a bunch of busy lines. The first lines are the blue lines, which are the contours where you get the correct value of the relic density for different values of theta. So if theta is 1, I get the right relic density at about 10 to the 11 GeV, decay constant. Theta is 10 to the minus 2, I get it at about 10 to the 15 GeV. If I allow theta to be as small as 10 to the minus 4, then I can get the right relic density all the way up to the Planck scale. This is just saying you can have large values of the axion decay constant if you allow for a moderate amount of fine tuning on the initial experiment. And you're still solving the strong CP problem because that has to get theta down to 10 to the minus 10. So, okay, so if you want to have all the relic density, you should live along one of these contours. I then do the same thing for the isocurvature amplitude. So for different values of theta, which are given by the same dot dashing, so solid is theta equals 1, dash 10 to the minus 2, dotted 10 to the minus 4. You have to lie below the red curves to satisfy the isocurvature amplitude less than 4% of the adiabatic amplitude. So where your two lines, red and blue, intersect, you have to be below both of those lines to have all the dark matter at that level of theta. So overall, you have to be below this black line that joins them. So if you want to have QCD axion be all the dark matter and be in scenario B, where this Peck-Schick symmetry is broken, so large values of F, You have to be below the black line. Everywhere, this is way smaller than the purple region. That tells you that the QCD axion in scenario B cannot be consistent with a measurably large value of the decay constant. I'm going to write this out in a little bit more detail in words coming on. Okay, so there is nowhere where you can have the QCD axion with large F be consistent with a measurably large value of the tensor to scalar ratio. And this is true for all F's once you take into account the relative density constraint that I mentioned before. This is true for all values of the decay constant larger than about 10 to the 12 GeV. So the QCD axion with decay constant larger than 10 to the 12 GeV cannot be consistent with ordinary tensor modes ever being measured in the CMB. Very powerful thing you can learn about the early universe. Here's now this plot in slightly different coordinates as made by Luca Visinelli. So he's now switched the X and Y axes around, but I think it's an easier plot to read otherwise. Hubble scale drone inflation, axion decay constant in GeV, different values of theta that you have to take in order to be consistent with the full relative density. So scenario B is large values of decay constant, small values of HI. Scenario A is small values of the decay constant, large values of HI. Everything in yellow cannot be made consistent with isocurvature. Or over here in scenario A, if the yellow is too, if you have large decay constants, you overproduce the dark matter. So scenario B up here, you need theta of 10 to the minus 4 at the Planck scale, then you can be consistent with Hubble of about 10 to the 10 GeV almost, but that's still a vanishingly small value of R, as we saw in this plot, that's here. Then as you take theta closer to 1, the value of F you need gets larger. And then this is the range probed by ADMX, which we'll talk about in lecture 9. So when Luca made this plot, we thought we'd measured R by bicep. So you could see actually in Luca's plot that if you measured the value of the tensor scalar ratio at about 0.1, you would not, there is nowhere where you would be allowed to detect axions with ADMX. So you see also this statement that in order to have the tensors and be in scenario A, F had better be smaller than about 10 to the 11 GeV. If F is larger than 10 to the 11 GeV, you have to be over here, which means you have to be at small values of H in order to be consistent with the isocurvature constraint. That's the point, right? You have to have small h to be consistent with isocurvature bounds if the decay constant is larger than about 10 to the 11 GeV.
Which I didn't really get that. Is it really in conflict with the theory, or can it just not be sourced by the Axion field?
Sorry, what is they?
Large on the bicep result. Would that be in conflict with the theory, or would we just add something?
Right, yeah. So the statement, and I think I have this in words in a few slides, is everything I have said is in the context of single field slow roll inflation, where the only source of large angle B modes is tensor fluctuations. So you can get around this statement by modifying your theory of inflation. But that would be really interesting, right? Because that's the point I'm going to make, is that, so what if we measure tensor modes R of 0.1 and ADMX detects dark matter, detects axions? That would mean this is all in conflict with single field slow roll inflation. So you would know something very non-trivial about the inflationary epoch if you detect both tensors and axions. So that's why they're very, I mean, if axions exist, they're a very good way to probe the early universe because of this kind of web of consistency that you have to have. So I'm just going to say that in words in the last few minutes. So the QCD axion in scenario B predicts a vanishingly small tensor scalar ratio, R less than 10 to the minus 9. That implies that measurements of R in the CMB would falsify the QCD axion in scenario B. If you measure R, scenario B cannot be true. A measurement of R in CME would require the QCD axion to be in scenario A, if it exists. Thus, you know that a K constant should be smaller than 10 to the 11 GeV. But these conclusions only hold for basic inflation models. So the detection of a high F axion as well as R, so if Casper or Abracadabra or even ADMX detect the axion, and we measure R anytime in the future, it implies a non-trivial early universe. So you could have beyond single fields for a roll. You could also produce large angle B. You can actually produce large angle B using an ultralight axion by refringence. So there are ways around this, but that you would know that it's not single field cell roll inflation, which is a huge thing to know. You can turn this around and you can say, well, can I use axions to measure the Hubble scale during inflation from isocurvature? So I've just been talking about improving the bounds on R and maybe one day measuring it. But you can also improve the bounds on isocurvature, and you could one day measure the presence of the isocurvature mode if it's there. Because as well as affecting the plateau, those locations of the peaks change ever so slightly. They're out of phase with the adiabatic mode, and they change the location of the peak. So you could measure the isocurvature mode, and then you can use axions to measure Hubble during inflation. So you need to. So in both of these cases, you need to measure two novel things: either measure tensors and axions, or measure isocurvature and axions. But in both cases, you can do something cool. So what if Hubble inflation is just really small? There's no reason it should be at 10 to the 14 GeV. It's a dimension-full parameter, therefore we should take a log flat prior on what its value is. It could be as small as a few GeV, because all we know is that the universe had to be reheated to an MEV to get BBN. Inflation could have ended at an MEV. So Hubble could be as small as a few GeV. We should not be biased towards this. If Hubble is that small, tensor-scale ratio is vanishingly small. We cannot measure it using B modes, but we can measure it using axions. So let's imagine that we detect axions and we detect isocurvature. The detection of isocurvature by CMBS4 can be used to measure the Hubble scale during inflation. And this is my last plot that shows you how you could do that. So I've plotted a band, which is the value of H inflation that is consistent with the Planck upper limit on isocurvature, but accessible to the CMBS4 projected upper limit. So CMBS4 will improve the bound on isocurvature by about an order of magnitude. If isocurvature is living there, then we can measure the value of H if we also detect axions. So if, for example, ADMX detected axions and S4 detected isocurvature, you would know that the Hubble scale during inflation is about 10 to the 7 GeV. If S4 detects isocurvature and Casper detects axions, Casper has a wider bandwidth, then you could infer that the Hubble scale during inflation was something like 10 to the 9 GeV. And you can put any axion experiment you want in here, but it applies particularly, as I said, to the large values of F, 10 to the 11, which have to be in scenario B. So all of this range, you can stick axion experiments in and imagine what value of H that would correspond to. So, I mean, it's a two-tooth fairies thing. You have to measure two novel effects, presence of isocurvature, and infer that dark matter is an axion. But you get a window onto the early universe that is not open from any other observable to low values of H. And yeah, you could do this with CMBS4 plus some axion experiments. So I like that. So values of the Hubble scale accessible in this way have very, very small r and are inaccessible otherwise. So that is all I wanted to tell you about today. We've covered CMB data, zeroth order constraints on axions from it, from the isocurvature mode. Tomorrow, we will begin on real constraints on axion dynamics from the CMB, so not just the mode structure, but in the adiabatic mode, how does the axion affect the shapes of these acoustic peaks? This will apply for ultralight axions. And then we'll take those further and bring these linear fluctuations of the CMB into galaxy formation and nonlinear physics in the late universe. So that is the end for today. But before we finish, are there any questions?
Question.
Yeah.
You said this next generation S4 ground-based telescopes. How would that work? I mean, the CMB is in microwave. How can we measure from ground? How can we measure from ground?
We always measure. There's lots of CMB experiments that already measure from the ground. Well, the CMB was discovered by Penzias and Wilson from the ground. And so you're worried about the atmosphere not being completely transparent to microwaves. Yeah, I mean, you model for the effects of the atmosphere, but yeah, you can definitely measure the CMB from the ground because that's how it was discovered. The ground-based telescopes do have to compete with more atmospheric noise. All kinds of things are harder from the ground. That's why the space-based missions always do big improvements. But for example, like you position the location of your telescope, you can choose to have, better or worse galactic foregrounds because of the location, things like this. You have to worry about the weather and things like that, but you can definitely do it. Yeah.
So going back to the last slide and the I think it was the scalar to tensor ratio. So why can't it be bigger than 10 to the minus 9? Do you assume that?
Well, what I'm saying is there is nowhere for axions in scenario B that is both consistent with the isocurvature amplitude and has R greater than 10 to the minus 9. So there's not a consistent point in parameter space with all the dark matter in a scenario B, Axion, and R larger than 10 to the minus 9. So that means that there is nowhere in parameter space for the QCD Axion with F larger than 10 to the 12 GeV that can be consistent with any measurable value of tensor to scalar ratio. Any more questions? If not, I'll see you all tomorrow. Thank you.